Welcome back. In this lecture, we are going to cover some aspects of the lithosphere, also known as the geosphere. Geology, which is the study of rocks, is a huge field, and we only have one lecture on it, which is why we are going to mostly focus on the unifying theory of plate tectonics. But we will mention a few other geological concepts and discuss the importance of the lithosphere or geosphere for the Earth system along the way. So let's get started. We're going to start off with a quick background slide on geologic time. The geologic timescale is a representation of time over a very long timescale. We, as humans, are not used to thinking on these timescales because they are so much longer than human generations or even human presence on Earth. But this is the timescale that geologic processes operate on. The different divisions are based on the rock record of Earth, so that similar Earth conditions and life forms are grouped together. Time is divided into eons, eras, periods, and epochs. This is shown well with the picture on the left. Time is denoted in millions of years, and different eons, eras, periods, and epochs are diagrammed out. Some interesting and significant developments for different times are listed on the right. The blow-up is just showing the Phanerozoic eon, since a lot of events humans tend to be interested in happen during this eon. I really like the image on the right too. It shows geologic time like the face of a watch. It is really helpful for understanding the relative amount of time different organisms have been on this planet. The colors in the main circle denote either eons or eras. Then there are circular lines on the outside that show when significant things occurred. There wasn't life for a very long time on this planet. This was during the Proto and Early Earth phase. This eon is called the Hadean because Earth looked kind of like a hellscape or Hades. Then simple microbial life evolved and was the only form of life for a very long time. The purple line labeled prokaryotes shows this. Eukaryotes evolved next. Eukaryotes are shown in the dark blue line. We are eukaryotes, but for a long time there were only single-celled eukaryotes and then very simple eukaryotes like sponges. Animals are in green, mammals are in orange, and dinosaurs are up there in the red line. Then hominins, like us, have been here such a short time that we can't really even be seen on the clock face. Now let's zone in on the Earth and its geologic organization. The Earth is made up of four major components: the crust, the mantle, the outer core, which is liquid, and the inner core, which is solid. There are different chemical and physical properties to each layer. The lithosphere is the cool, rocky outer part of the Earth, its rigid shell. This is a confusing point because we also refer to the lithosphere as one of the four spheres of Earth. The lithosphere that is a sphere of Earth represents all land and so includes the layers beyond the actual lithosphere shown on this image. While we interact with the uppermost layer, which is the lithosphere, the layers are all connected, and we will talk about how in this lecture. Because of this, some Earth scientists call the sphere of Earth that deals with land the geosphere. Anywho, the lithosphere goes from the surface to 100 kilometers or 62 miles. It is made up of the brittle crust and the brittle topmost part of the mantle. The asthenosphere is the denser, weaker layer beneath the lithospheric mantle. It goes from 100 kilometers to as deep as 700 kilometers. The temperature and pressure is so high that rocks soften and partially melt, becoming semi-molten. This allows it to flow like a thick fluid, which is important to plate tectonics. Earth's crust is made up of a range of chemical elements. The top four most abundant elements in Earth's crust, by weight, in order, are oxygen, silicon, aluminum, and iron. The graph to the right shows the abundance by number of atoms on the y-axis and sorts elements by the atomic number on the x-axis. The rock-forming elements are circled in green, and they are obviously all very abundant in Earth's crust. There are actually two types of crust, continental and oceanic. First is continental crust, which is made mostly of granite, which is a type of igneous rock. It is less dense and lighter, which causes it to be thicker and to float on top of oceanic crust when the two meet. It is about 30 to 50 kilometers thick. It is also older than oceanic crust because it doesn't get subducted and recycled like oceanic crust does. That is a reference to the rock cycle, which you may have learned about in school before. We aren't going to learn much about the rock cycle beyond the fact that some rocks can be subducted, at which point they enter the asthenosphere, where they are melted down, forming magma, and eventually come back to the surface as igneous rocks from volcanic activity. Next is oceanic crust, which is made mostly of basalt, which is another type of igneous rock. It is denser and darker. It is about 5 to 10 kilometers thick. It's also younger or newer than continental crust since it is continuously being made at mid-ocean ridges and subducted at convergent plate boundaries, We will cover the different plate boundary types later in the lecture. Before knowing about plate tectonics, which we haven't actually learned about yet in this lecture, but we will, Alfred Wegener proposed the continental drift hypothesis. He noted the puzzle-like fit of modern continents. See how the east coast of South America looks like it could fit along the west coast of Africa? Well, he proposed that the continents were able to drift around. Like many groundbreaking ideas, it wasn't well accepted at first, but there was a lot of evidence for it. In addition to the way that the continents look like they could fit together, there are similar fossils on very different continents that are best explained by the continents being connected in the past. Today, the continental drift hypothesis has been absorbed into the theory of plate tectonics, since plate tectonics actually describes the mechanism for how continental drift works. The implication is that continents have been constantly moving around for the entirety of their existence. There have been many supercontinents throughout Earth's geologic history. The most famous was called Pangaea. It was one large supercontinent that existed 200 million years ago. Penthalassa was the one large ocean that existed at this time. Here are some cool links that let you explore the arrangements of the continents in the past. I put some pictures up too, but you can explore a range of times using these links. Now that I've hinted about, name-dropped, and teased learning about plate tectonics, let's actually learn about it. The lithosphere, which is the cool, rocky outer part of the Earth, is divided into plates that move on top of the fluid mantle, driven by mantle convection. You can see mantle convection currents on the right, visualized by the white circular arrangement of arrows. In some areas of the ocean, there are mid-ocean ridges, which are spreading centers where new crust is made. This is also known as a divergent plate boundary, an area where two different lithospheric plates move away from one another and magma seeps to the surface in the crack that is formed and makes new oceanic crust. There is a ridge because the seafloor is hot, making it less dense, so the rock is expanded, forming a ridge. Like I said, magma comes to the surface at a fissure vent. This is a type of volcanism. Shield volcanoes can also form. These are not particularly explosive volcanoes, meaning they typically don't create massive blasts that destroy civilizations. In the upper image, the mid-ocean ridge is visualized by magma coming to the surface. You can see the ridge running away from the cutout. There is a horizontal fault running through the middle of the mid-ocean ridge, but that isn't the ridge itself. If new crust is being made, then it also has to be destroyed somewhere, and that happens at subduction zones. Subduction zones are convergent plate boundaries, and this is the site of crust destruction. Subduction zones generate deep ocean trenches like the Marianas Trench. It also creates earthquakes and volcanic arches of stratovolcanoes, sometimes called composite volcanoes. These are the most violent type of volcano on Earth. There are earthquakes because the heavier oceanic plate is being dragged under the continental crust or the continental plate, and this creates a lot of friction. Then the subducted rocks melt at high temperature and pressure, and buoyant magma floats to the surface with explosive results. That is why there are huge arcs of volcanoes nearby. The exact chemical composition of magma also affects explosivity. Note that hotspot volcanoes, like what Hawaii has, which is a shield volcano, are not associated with plate boundaries. They occur in the middle of a plate, kind of like a zit. There are other volcanoes as well, but we won't discuss them. The implication of divergent and convergent plate boundaries is that crust materials are being recycled, and this is actually a key factor for habitability on Earth. Here's a great map that shows all the different tectonic plates on Earth. You can see the names of the different plates and the general way that they are moving. You can see that all along the Atlantic Ocean there is a divergent plate boundary, where new oceanic crust is being made. There are other divergent plate boundaries as well. There are also many areas where tectonic plates ram into each other, forming convergent plate boundaries. Finally, there are transform plate boundaries, where plates slide past one another on the Earth's surface. I live in California, and we have a large transform plate boundary in California. This will cause earthquakes, but the earthquakes aren't as deep as those at convergent plate boundaries, and we don't get volcanic activity because of them. Most spreading centers are in the ocean, but not all. There are some continental divergent plate boundaries called rift valleys. One such rift valley is in Iceland, where the divergent plate boundary that runs all along the Atlantic Ocean continues through Iceland. Shield volcanoes are common at spreading centers. I mentioned it before, but this map shows it really well. Earthquakes and volcanoes tend to occur at plate margins and have helped us to identify them. Most large earthquakes occur at subduction zones. Earthquakes are marked in orange on the map. There can certainly be earthquakes along other types of plate boundaries as well, but the really big ones tend to occur when two plates run into each other. It is the same with volcanoes. Volcanoes are marked in red on the map, and they tend to occur at subduction zones. The Ring of Fire is a region around much of the rim of the Pacific Ocean where many volcanic eruptions and earthquakes occur. The Ring of Fire is a horseshoe-shaped belt about 40,000 kilometers long and up to about 500 kilometers wide. We know that new oceanic crust is formed at mid-ocean ridges and old oceanic crust is subducted at subduction zones, and we can plot seafloor age on a map with this knowledge. Remember that oceanic crust is denser than continental crust. That means that when oceanic and continental crust meet at a convergent plate boundary, oceanic crust is subducted. That means oceanic crust can't get too old. And of course, it is constantly being made at mid-ocean ridges. There are lots of spreading centers, but one of my favorites is in the Atlantic Ocean because it is so long. The Atlantic Basin is about 6,000 kilometers wide, but is getting wider by 1 to 10 centimeters per year because of spreading. If we wanted the oldest oceanic rocks, we would look near the coasts. You can see that the colors are typically blue and purple near the coast. Then the youngest oceanic crust is obviously along the mid-Atlantic ridge. You can see the colors are all red along the mid-Atlantic ridge. Now let's talk about the age of continental rocks. Continental crust is less dense than oceanic crust, so it does not get subducted at convergent oceanic continental boundaries, which is shown in the top image on the left. This means that it can get much older than oceanic crust. Note, one plate eventually gets subducted during continental convergence or collision, which is shown on the bottom image on the left, but large mountains are made via orogeny. The Himalayas are an example of what happens during a continental collision, and orogeny is a process in which a section of the Earth's crust is folded and deformed by lateral compression to form a mountain range. It is the primary mechanism by which mountains are formed on continents. Some parts of the continents are composed of very old rocks. These are known as cratons. Some cratons in Greenland and Canada shelter rocks that are 4 billion years old. The map on the right shows some cratons in North America, and some areas are older than 2.5 billion years, and this also includes the rocks that are 4 billion years old. So where does plate tectonics get its energy from? Plate tectonics is fueled by Earth's internal heat sources. This comes from a combination of leftover or primordial heat from Earth's formation, and also radioactive decay of radioactive elements in Earth's interior. This causes giant convection currents in the mantle as the heat is redistributed by the liquid rock moving around. Heated mantle material is shown rising from deep inside the mantle, while cooler mantle material sinks, creating these giant circular convection currents. This pulls the overlying tectonic plates around. You can see the direction of the convection current leads to either convergent or divergent plate boundaries. Plate tectonics creates topography and bathymetry. Topography refers to the elevation and arrangement of landforms, and plate tectonics creates mountains and valleys. There are definitely other factors that affect topography as well, but plate tectonics is the big picture stuff. Bathymetry is topography of the seafloor. Again, plate tectonics drives bathymetry. It causes deep ocean trenches and mid-ocean ridges. Now let's talk about a specific example, North America and the Sierra Nevada, which is the mountain range running along a majority of the state, shown in orange there. Currently, the Pacific Plate is traveling north, while the North American Plate is traveling south along the San Andreas Fault. This is a transverse fault. However, in the past, this used to be a convergent boundary. The Sierra Nevada are actually the eroded remnants of the volcanic arch that developed when the Farallon Plate, an ancient oceanic plate, subducted beneath the continent. There is a related concept to topography and bathymetry, which is called Earth's hypsographic or hypsometric curve. This is the cumulative height frequency curve for the Earth's surface, or some part of Earth's surface. It doesn't have to be for the entire planet if you're just interested in one particular coastline or even an inland lake. It is a graph that shows the proportion of land area that exists at various elevations by plotting relative area against relative height. That's what we're looking at here with the bar graph, the vertical bar graph on the left, with brown being above sea level and the blue being below sea level. You can see that a majority of the above sea level land occurs right near sea level. It's just above it, whereas a majority of the land below sea level occurs at kind of intermediate depths and also towards the surface. The hypsographic curve for Earth has changed significantly over geologic time due to sea level change and due to plate tectonics. If you want some more background on either continental drift, plate tectonics, or hypsometric curves, these are some helpful YouTube videos. So now that we've talked about how new oceanic crust is made, old oceanic crust is destroyed, and how continental plates move around, we are ready to talk about the Wilson cycle. The Wilson cycle is the process of the creation and destruction of entire oceans or ocean basins. The continents move around as this happens. One cycle takes about 500 million years. Remember that geologic or tectonic processes are very, very slow. The Wilson cycle is named after John Wilson, and it is a plate tectonic model. This graphic has a good step-by-step process. Like I said on the last slide, it describes the formation, growth, and destruction of ocean basins and explains why continents come together and move apart. The Wilson cycle also affects Earth's hypsometric curve. Plate tectonics is key to Earth's habitability. Plate tectonics is responsible for the recycling of substances between the solid Earth, the atmosphere, and the hydrosphere. Long-term climate regulation is actually due to a feedback involving volcanoes and rock chemical weathering. This is a process that does not involve life, and we will cover it in a different lecture. Plate tectonics is also important for accumulating large amounts of oxygen in the atmosphere. Again, this will be talked about in a different lecture. The last thing we are going to talk about in this lecture is Earth's magnetic field, which is caused by Earth's outer core. Earth's core is made of iron and nickel. The inner core is solid while the outer core is not. A magnetic field is generated by electric currents due to the motion of convection currents in the Earth's outer core, which is caused by escaping core heat. This is important for habitability because the magnetic field protects Earth and life on it from harmful solar wind and cosmic radiation, and because it protects Earth's water from being lost to space. Plate tectonics also appears to be required for a planet to have a magnetosphere, which is generated by Earth's magnetic field interacting with particles from solar wind in Earth's upper atmosphere. And so this is actually another way that plate tectonics makes the Earth habitable. That concludes the material. Let's go through and review the main points. Earth's crust is composed primarily of oxygen, silicon, aluminum, and iron. Earth has concentric layers or shells. The theory of plate tectonics explains Earth's geologic features and activities. It also states that Earth's lithosphere is composed of rigid plates that move with respect to each other on a liquid mantle. It occurs slowly but has caused massive changes in Earth over geologic timescales. Crust is created at spreading centers called mid-ocean ridges and is destroyed at subduction zones. There are many different forms of evidence for plate tectonics. The Wilson cycle is a cycle of creation and destruction of ocean basins. Earth's hypsometric curve has changed over time. Plate tectonics is important for habitability because it helps recycle crust materials and substances from the atmosphere and oceans. Plate tectonics also participates in a long-term climate stabilizing feedback covered in a different lecture. The Earth's magnetic field is created by convection currents in Earth's outer core and is another key feature for its habitability. Plate tectonics also appears to be connected to a planet's ability to produce a magnetic field, which protects Earth, its water, and life from harmful solar wind and cosmic radiation. Thanks for sitting through the lecture. To test your learning, I suggest you review the material and make sure you can answer these questions.